Welcome back from spring break. This is UBC CS 532 W 539 something, who knows, probabilistic programming, graduate level, so on and so forth. Good job on the homeworks. Most everybody did okay. We should return to this in a little discussion at the end. Everybody should be talking amongst each other to get best practice in terms of implementations. Baron might optionally say some things at the end about feedback on how everybody did and which of you need to maybe think about stealing other people's implementations for the next homework to build on top of anyway. So today we're going to talk about Hamiltonian Monte Carlo. I also already warned Baron. How many of you have physics backgrounds? Ish. Okay, good. So except for Baron, I think this will be acceptable for all of you. For Baron, this lecture is going to be hideously painful. And Baron, please feel free to speak up once we hit like Liouville's theorem and these sorts of things that are not in my well, yeah, you'll see it. There's some embarrassing physics in here, but it'll get the job done. To remind you, since we've been away from each other for so long, we're at the point where we've got a first order. We know what inference is. Blah 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 blah. We've got a first order probabilistic programming language, and you all, congratulations, now have written in many of your cases the first evaluator you've ever written. Some of you have done that before, but not all of you. Good job. That's totally cool. But the evaluator that we did was only to evaluate the joint or prior distribution, really, of the latent variables, which is not what probabilistic programming is about. And the next homework is the first probabilistic programming system that you will fully implement. And as Baron said to me in our meeting earlier today, get started. If you haven't, don't wait until the end. Some of you, maybe starting with N and then ending with I and then with an AOM in between, might not have started the last homework until a little bit later than they needed to, and we don't want to see these sorts of things happen again. So hop on it. It's how did you describe it? It's doable. I apologize if that is not a safe space thing to have done. I didn't call anybody out. I just said some letters. That's all. Right? So Baron, how did you put it? Doable, but what's the effort level like on this next one?
I think it's all fine. Like, it's all there. Like, nothing is incredibly hard. It's just, it'll take some time. Like, you'll find some things that you thought weren't there and you'll have to fix them. So I really suggest to get started, especially because there's office hours tomorrow. So you can maybe have a look at it tonight and ask some questions tomorrow. Yeah, I'm happy to answer some.
When is the homework due? Please check the schedule, the syllabus. It's on the syllabus. So anyway, and again, I would recommend this very much builds directly on the last homework, like I sort of threatened at the beginning of the course. So you are 100% totally allowed to take somebody else's code base and build off of their code base, right? And I think, oh yeah, there's somebody we can make fun of. I thought Jason was here already. I think Baron pointed out that there's several really good implementations, but on the Python side, Jason's implementation was particularly strong, so you could reach out to Jason. And I think out of the two Julia implementations, I think Adam's won. So if you want to compare and contrast and get in each other's code bases, please do. The point is to learn, not to call people out and make people feel bad. Now I feel terrible, Naomi. Please, can you tell me that you feel okay, like not terrible?
I'm never gonna recover.
Oh God. Oh man. All right. I apologize. Okay. Again, the point is to learn. That's really the point. Okay. So where are we? Sample from the joint. Now we're going to actually build prog systems that do inference. Okay, so you know how to write graph-based and evaluator-based IS. In lecture 10, what we did is we talked about important sampling engines for the graph-based and evaluator-based representations of the underlying program. And we talked quite a bit about Metropolis within Gibbs sampling for the FOPL, spending a fair amount of time on this. I mean, you know how to do Metropolis within Gibbs because it was on the first.
Just interject before we get too into this.
Yeah.
Reiterate what Payman asked in the chat. Because homework 3 is due in 2 days.
Is it due in 2 days? Yeah. Well, I guess you should have started. Really? We'll return to this at the end of.
No numbers, but it says 225 on the syllabus.
Okay. Yeah. Well, yeah. That was the due date because we need you to be getting things done. So hopefully you will have started homework 3. A lot. The only thing that you need is today's lecture, and today's lecture covers something that is actually relatively easy to implement. So chances are it will move, but it can't move that much if we want to actually get through the course material. That's the issue. What I don't want to have is the homework overlap with the course project, because the course project is what I actually want all of you to actually focus on. So it'll move, but not a huge amount. Anyway, so Metropolis within Gibbs, you did that in the first homework, right? Implemented Metropolis, implemented Gibbs sampler where the individual conditional distribution samplers are implemented and via Metropolis Hastings. So the idea that we talked about was to Gibbs sample through the conditionals, where you have every random variable in your program. And this is just this is like a definition of V here. We had the discussion about the free variables surrounding like X, so the free variable surrounding X, whatever that happens to be, and those would be the expressions that have X in their body, basically the variable name X in the link expressions, and of course implicitly that will pull in this. So when you evaluate the Metropolis Hastings acceptance ratio, both the numerator and the denominator, you will effectively be evaluating some expression which evaluates to the density of the Markov blanket around X. And of course, you have the option of what to propose, and what to propose, you can just actually take the prior expression for X. In other words, whatever the link expression is here, you can use that as the proposal and you're golden. Although you need not do that, you can choose to use custom proposals. So this is just, we already did this, I'm just reviewing it. But if there are questions, feel free to ask them now. Because this next homework, just to be clear, is important sampling, MH within Gibbs, and HMC. So 3 different inference algorithms. I saw that some of you in the second homework did important sampling already. That one's pretty straightforward. These 2 are, again, not hard, but actually require a little bit of thought if you're unfamiliar with sampling. Okay. How many of you have started homework 3? Okay, that's bad. Please start. Great. You all have, because you did homework 2. That is a start to homework. That is a start to homework 2. Cool. So Metropolis within Gibbs, and then algorithmically, what's going on? Just to be clear, Metropolis within Gibbs, you Gibbs cycle through the conditionals, and you sample from each of the conditionals, right? That's this algorithm here. Here's an initial state of all the latent variables in your program. This is a number. Again, this is going to be a stream, but this would be a number of samples. And what you do is, for some number of samples, in other words, forever yielding, right? You take a Gibbs step from the old state and you update the state, and then you return the stream of states. And Gibbs step, what does it do? It takes the dictionary of latent variables, and for every latent variable in that dictionary, you look up from some dictionary of proposal expressions. Again, this can just be the prior expression for that variable. and you evaluate that expression with all of the variables bound to their values in this dictionary, right? That then you copy the state, you set the value for that random variable in the new state by sampling according to the proposal distribution, and then you evaluate the acceptance ratio that we have talked about in the previous slide, and then just do the Metropolis Hastings thing. The acceptance ratio says evaluate the proposal in each of the two states, x and x prime, and then compute their log ratio, then get the Markov blanket and evaluate the joint probability of the Markov blanket expressions on top and bottom, constructing the correct log density ratio. Okay, that makes sense? Any questions here? This is just a review of where we were, but all of us are coming back from spring break and we have to get our heads back into the game. So questions? Naomi, can I get back on your good side by answering a question here? Yeah.
I don't have a question. Sorry, maybe later.
Okay, great. Okay, cool. Payman, can I get you ungrumpified by answering a question here?
That's just how my face looks like.
Okay. All right. I guess I'm
sure this ends up in the recording.
I'm on the path of offending everyone today. Okay. I think I'll just try to offend literally everyone. That'll be good. It comes very naturally to me. Don't worry. Okay. So today we're going to do Hamiltonian Monte Carlo, and the learning goals are to understand roughly how Hamiltonian Monte Carlo works. It's actually, you could do a whole course on Hamiltonian Monte Carlo. So we'll just try to get the idea across. You should be able to, at the end of this lecture, have enough understanding of it to write a Hamiltonian Monte Carlo sampling engine for the FOPL. And if you really get into this, then I highly recommend that you read the two references here, in particular Neil's original reference on Hamiltonian Monte Carlo, which is really absolutely lovely to read, and no lecture can do as well as that. Anyway, but before we get started, I actually thought I found this thing when I was trying to figure out whether or not I could improve my way of talking about Hamiltonian Monte Carlo, which I think is like an amazing. I don't know who wrote this, but I think the person's name is there probably on their Git repository handle thingy. But there's this amazing thing which will help explain what's going on, particularly in Hamiltonian Monte Carlo. And I want you to have this picture in your head, because really I was going to draw some pictures of balls rolling around in energy potential wells and that sort of stuff. And I'm like, well, wait a second, why don't we just look at this? So let's look at random walk Metropolis Hastings, what's happening. So here we have some unnormalized posterior distribution, right? And what happens when you're doing Metropolis Hastings? So again, we have an unnormalized density. This is our probabilistic program. And when we're doing Metropolis Hastings, we have some proposal. And pretend for a second we have our proposal for the entire program, right? All the random variables simultaneously. And what's happening here is we already did this. This is just Metropolis Hastings, right? You know that there's a proposal distribution. That's the isosurfaces here. There's a step proposed, and then it's either accepted or rejected. It's rejected when it's red, rejected when it's red, rejected when it's red, rejected when it's red, accepted when it's green, okay? And so on and so forth. And you keep doing this over and over and over again. And the Markov chain, as we talked about in the beginning of the course, is constructed such that it, in the long run, equilibrates as a set of samples that well approximates the entire distribution, right? Okay, so that's random walk Metropolis Hastings. And of course, you can choose a different proposal kernel size, and you're going to get a different acceptance ratio. The sampler will be more or less efficient depending on how large your proposal size is, or so on and so forth. You get lots of proposals, but it takes a very long time for this, particularly if you make the proposal size really, really small, then it's going to take a very, very long time for this to explore the entire space. Okay, more to the point. Okay, so this I think is fine. we can also look at, just for the fun of it, Gibbs. Okay. And you should have this idea in your head as well, that basically what ends up happening is that it never rejects, right? Because we know that a Gibbs kernel is a Metropolis Hastings kernel that accepts with probability 1. But what's going on is that at every step, you make a conditional distribution, a draw from a conditional distribution in one axis, and then a draw from a conditional distribution in another axis. So the way it walks around the density is very, very different and much more efficient because you're sampling from the conditional distribution at a particular point in space, the complete conditional distribution. Okay. Now, that's not, so we're doing Metropolis within Gibbs, so we're going to have an inefficient walk, but an efficient outer loop. Okay. So that's Metropolis within Gibbs, right? This doesn't have importance sampling because there's no reason for importance sampling. But what it does have is Hamiltonian Monte Carlo, and I think that's super, super helpful for understanding what's going on. Okay. So now maybe Naomi will have a question that I can get back on her good side by asking or answering or whatever. So this is what Hamiltonian Monte Carlo should look like in your head when we're talking about what's going on today in class. Which is to say that we are going to construct, we talked about auxiliary variables in the beginning, like we had a slice sampling as an auxiliary variable trick. Hamiltonian Monte Carlo is an auxiliary variable trick. What you can't see here, except in the form of these little gray arrows, are an auxiliary variable, which is a momentum, okay? So we're going to jointly sample by choosing a random momentum that's indicated by this gray vector, and then numerically integrating along a constant energy isosurface of a Hamiltonian that dynamically trades between kinetic and potential energy, okay? So what you see here, you can think of the little black trajectories as a ball that is rolling along. Just invert the density and think about it as like a bowl, right? So you kick off the ball with some energy, and then let the ball roll according to the natural laws of physics that trade off potential and kinetic energy deterministically, fully deterministically. Okay, and then at the end of the trajectory, because we're going to not be able to integrate these trajectories, the set of differential equations perfectly, you will arrive at some other state which is very, very close in total energy to the original state. And we take a small Metropolis Hastings, we correct with a small Metropolis Hastings correction ratio. So in other words, there's an acceptance probability because there's a numerical integration scheme involved. But the point is that because of these deterministic dynamics, Hamiltonian Monte Carlo algorithm will typically, in these kinds of continuous spaces, mix much, much more efficiently. So if you see what's going on here, right, relative to, for instance, Metropolis Hastings with a small proposal, the rate at which one sample goes to the next sample in the chain, mixing over the entire space, is much, much higher for Hamiltonian Monte Carlo. Okay. Does that make sense?
Can I ask a question?
Please, yeah.
I guess I have two questions.
What's that?
Are the number of black dots, like I guess steps, the same for each big step?
So the intermediate black dots are thrown away. They are not samples.
But does each step have the same number of intermediate steps?
So in this particular case, yes, these are known as leapfrog steps. So you can see the number of leapfrog steps here is 37. I can make the number of leapfrog steps smaller. In theory, so that's now 13 leapfrog steps.
Okay.
And again, what you can't see, like physical intuition actually works quite well here. If you imagine that gray vector is a push of the ball, and you look at this density as being a bowl, you can sort of watch what's going on here again. So
is it, in that sense, is it similar to like the momentum methods in optimization? Like
they're indeed, yeah. So
each step is like partially solving one of those?
There,
You cut off the
intuition is
number
the
of-
same. It's not. It's not quite the same as like a heavy ball method in optimization. But the idea that there is a momentum is the similarity, right?
Okay.
Okay.
Thanks.
Yeah. Okay. Cool. I could just sit and watch that. You basically learn everything you need to know about Hamiltonian Monte Carlo by just. That's amazing that Jason is drinking from something that doesn't exist. When you drink, it goes away. Or it did. Yep. There you go. Okay. Cool. All right. So too long, didn't read. Hamiltonian Monte Carlo is an efficient Monte Carlo sampling scheme that uses gradient information advantageously. Okay, so this sort of straight away, your ears should perk up and think Bayesian deep learning or differentiable models only, so on and so forth. There's going to be some restriction on what we can do here, but it's powerful enough that probably the most utilized probabilistic programming system, period, called STAN, is entirely reposed on Hamiltonian Monte Carlo. It's the only inference algorithm that's available, and everything is assumed to be differentiable. The joint density is assumed to be differentiable with respect to all of its latent variables, which we will see much later in the course is not something that you can always assume. Certainly already in the assignments that you have seen, that's not true, for instance, for the HMM assignments. So HMC applies to differentiable joint distributions with respect to their latent variables. It does not work well on all models with branching. So there's been some pretty heavy lifting work done on this. I credit this guy largely for figuring stuff out, but he let me be last author. That's totally cool. So if you're interested in this and like how to work on Hamiltonian Monte Carlo in probabilistic programs with discontinuities, you can think, how do you do Bayesian deep learning in neural networks with ReLUs, for instance? There's lots of project ideas available there. So another thing that a way of thinking about things, you can think about Hamiltonian Monte Carlo as an efficient block proposal. So if you did a static analysis of your probabilistic program and you could find subsets of link functions whose collective conditional joint distribution, in other words, the Markov blanket of that entire set of variables is continuous, is differentiable with respect to the latent variables in that block, then you can think of Hamiltonian Monte Carlo as being a very, very efficient Metropolis Hastings kernel for a block Gibbs sampler in which the entire block is different. The Markov blanket of the block is differentiable with respect to the latent variables in that block.
Could you quickly remind me what branching means?
If you have an if statement.
Okay.
Or discrete random variables, those two things are equivalent. Or in the case of Hamiltonian Monte Carlo, you could think in optimization land, if you have a probabilistic program with branching, programming language with branching, is, in particular, the way we set it up in this paper, is differentiable almost everywhere. So if you're interested in doing optimization in spaces in which, except for a measure zero set of discontinuities, everything is differentiable, then that's what this paper describes, is a language that describes such effectively optimization problems and how Hamiltonian Monte Carlo works. And then there are variants of Hamiltonian Monte Carlo that work better when you're in a space like that. Okay, so I'm going to use two different notations today. I apologize for that, but I just want to put the Hamiltonian Monte Carlo in book notation. We'll come back to this. They're very closely related. It's going to be okay. The two notations are very, very closely related, but I just want to put Hamiltonian Monte Carlo in book notation out in the beginning, and we'll talk about the implementation of it and that sort of stuff, and then we'll go through some of the maths relatively quickly. So let's assume that we have an unnormalized target. Again, this is the posterior or whatever. So this is the thing, right? And it's equal to the joint, right? Evaluated with the observed values fixed, right? Divided by some unknown normalizing constant, right? Fine. So this is just an unnormalized density, an unnormalized posterior. Hamiltonian Monte Carlo refers to Hamiltonian, where there is a potential energy which corresponds to the log of the unnormalized density, this thing right here, right? So the log joint density, right? With the values of y plugged in. There's a total system energy, which is the potential energy plus some kinetic energy. That's the Hamiltonian, right? Where usually in Hamiltonian Monte Carlo, the kinetic energy is formed basically a mean field. You make a mean field assumption, but basically it's a diagonal Gaussian kinetic energy, and we'll see what that looks like. I don't know why this is there. That's why it's like that. Okay, so this unnormalized unnormalized target is actually an auxiliary variable distribution in which the original potential energy corresponds to the model, and there is some kinetic energy distribution that depends on that's a function of some other random variable r. And now the question is, how do we evolve this system? So we'll get into this, but that's the book notation. Now we're going to switch to a slightly different notation. We'll come back and it'll be really obvious. Don't worry. Okay. So here's the assumption. You'd like to sample for some distribution P of x, which is some unnormalized density, okay? And we're going to assume that P twiddle of x is, differentiable with respect to all elements xi of x, okay? So you can just forget the Prog thing for a little bit, just think vectors. That's why I want to do the notation. Just think vectors. It's going to all apply in the Prog case. So x is some vector consisting of a bunch of xi elements, right? And we have some distribution from which we'd like to sample P tilde, which is unnormalized. So you can think of this as a posterior distribution. So Hamiltonian Monte Carlo creates a physical system that adds momentum auxiliary variables Pi, one for every dimension of x. Okay, so again, just x1, xi, who knows, xd. I don't even know what I use for xd. Doesn't really matter. And then simulates the time evolution of such a system in such a way that the set of recovered positions, the endpoints of these trajectories that you were seeing before, constitute valid Markov chain Monte Carlo samples from the distribution of interest, that being P tilde, and can potentially have low autocorrelation, which is to say they're basically nearly independent. So if you were to look at the chain of samples that come out of your Metropolis within Gibbs algorithm, they're going to be highly, highly correlated. Hi, Mia. So basically the idea is that they'll potentially have low autocorrelation because of the dynamics, because the dynamics will allow the state of the sampler to move dramatically in the state space, in whatever space X lives in. You're going to be able to move really far distances in that. Okay. So here comes the crappy physics. Get ready. It's going to be fun. Okay. So there are a couple of things that you have to remember from physics and multivariate calculus before you can understand what's going on in Hamiltonian Monte Carlo, and we'll get to most of them, not all of them. Okay. So from physics, high school / early college physics, we need a couple of things. First, we need to know that momentum is mass times velocity, and the velocity is the time derivative of position. So you can write down momentum as mass times velocity, or mass times the change in x over change in t, the time derivative of the position. We also need to remember that force times mass force times mass. Force equals mass times acceleration. And acceleration is a change in velocity over time. Okay, cool. So with these little bits, you can get that the force is equal to the time derivative of momentum. So F equals ma, we all know that. A is the time derivative of velocity, and so long as the mass doesn't change, so we're like in Newtonian physics here, not in relativistic physics, right? So long as the mass is not a function of time, then you can pull the m in, and that's just F is just the time derivative of the momentum. Okay. We also have to make use of the following definition. Right? A conservative force is dependent only on the position of the object. If a force is conservative, it is possible to assign a numeric value for the potential at any point. When an object moves from one location to another, the force changes the potential energy of the object by an amount that does not depend on the path taken. Okay? So there are a bunch of, there are, I think, 3 equivalent definitions of a conservative force, but a force is a conservative force if it can be written as the negative gradient of a potential field. Okay, so there's some potential field, right? You can think of this as this is going to be the joint density, right? Except upside down, right? So there's a potential field, and the force is the gradient in that potential field. Okay. Makes sense. So the Hamiltonian is an expression for the total energy. So notation will be h of x and p of a system whose joint state, whatever that happens to be, again, these are going to be the latent variables in our system, x has a potential energy, u of x. This, again, you can think of as the unnormalized joint distribution or unnormalized posterior distribution, and some kinetic energy, which in our case is going to be a made-up auxiliary variable. Okay. Cool. And we can write the Hamiltonian as the kinetic energy plus the potential energy. Great. And of course, you'll be used to, from again high school physics and first year Newtonian physics in college, that kinetic energy comes in the form of an equation like 1/2 mv squared in some system, right? For whatever the thing is. And you should note that you can equivalently write 1/2 mv squared as 1/2 p squared over m. So writing the kinetic energy as a function of momentum is no big deal. Okay, fine. Okay, so many of you probably have intuited or know or have heard that the energy of a system or the Hamiltonian of a system corresponds in a statistical physics sense inversely to its probability, right? That's maybe not terribly surprising if you think about it. It's intuitive anyway. The canonical distribution corresponding to a given Hamiltonian is literally just here's the probability of the state xp being the probability of a particular configuration of a system, right, is equal to e to the minus Hamiltonian. Right? In this particular case, that will be e to the minus potential energy and e to the minus kinetic energy. Now, how does this work out, right? Just to be clear again, or to preface what's going to go on, this is going to be u of x is going to be log p of x given y, something like that, right? So the e is going to cancel with that. So you can already see that that one part of this joint distribution is just the original probability that you're after, and depending on the form of this, no matter what. It's clear that x and p are independent quantities in the statistical sense, right? And certainly when you start thinking about Hamiltonian Monte Carlo or Gibbs distributions or Boltzmann distributions or anything like that, it should be reasonably acceptable to believe that high energy states are low probability and vice versa, right? don't want to go into much more than that here. But it's clear from this formula that that's true. Yeah.
I'm struggling to see why X and P are independent, because P, like from a physical perspective, depends on, like, it's based on the derivative of X.
So the momentum of a particle and its position need not be dependent on one another.
Okay.
Right.
I guess it's
Right.
to get
Just thinking about a ball, right? You know, its position can be totally independent of its momentum at that position, right? So
yeah, I'm just okay. Never mind.
So you could form a Hamiltonian in which this is not true, and that would be weird physics, right? And I'm sure this is the point at which Baron could pop in and say, yes, there are weird physics that you have to pay attention to this, right?
Well, I was going to say in quantum physics, this is clearly not true, right? That's the whole point of quantum physics. That at that point, momentum does say something about position, but.
Indeed, Heisenberg had something to say about this in like 1920 or whatever, 1910. Yeah, so yes, indeed. But again, I did say Newtonian land. We're in Newtonian land, right? So we're in Newtonian land, which means I've got this pen. It's got a position, and I can give it whatever momentum I want at that position, and those two things are totally independent from one another, right? If we consider the wave function of this pen, it's pretty tightly peaked. So, I'm not terribly worried, right? But just in terms of like looking at the expression, just to be clear, right? What does it mean for two things to be statistically independent when you look at a joint distribution? It means that, P of xy is equal to P of x times P of y, right? And that's exactly what's going on here, right? So just by making this assumption, you can think of this as an assumption here because we're making an assumption basically, right? That the joint distribution and in fact the Hamiltonian decomposes in this way means that x and p are statistically independent. Okay. Cool. Yeah. Yeah. Okay. So in addition to all the stuff we've gone through so far, we're going to assume a particular form for the kinetic energy, okay? Which is to say that there's these auxiliary variables p, and we're going to say that kp it takes the form it has a quadratic form. It's a quadratic form, right? Which, in particular, if you assume that m here is a vector, right? Then you can rewrite this quadratic form as just basically the sum across the diagonal of a bunch of independent Gaussians. This is basically the unnormalized form of a bunch of independent Gaussians. Everybody okay with that? I want to take that as a yes. Okay, great. So that further means that the kinetic energy of the system decouples into the sum of the individual kinetic energies of all the dimensions / particles. Totally fine, right? This thing in here is referred to as a mass matrix. So if you make this assumption, in particular that it has this form, then it implies that the momentum variables p are normally or multivariate normal distributed with a diagonal covariance. Okay, you can change that. There's a lot of work on learning this mass matrix for various problems. You can do adaptive Hamiltonian Monte Carlo where you learn this. This mass matrix is actually super important for having success with Hamiltonian Monte Carlo in particular, because it says something about the length scales in each dimension of your system. But that's a detail that we can leave for some other time. So part of what Hamiltonian Monte Carlo does is that it evolves the state of this synthetic auxiliary variable system with the Hamiltonian that we've been talking about deterministically at a fixed total energy. And just like the ball example that we saw in the plots earlier, it basically by doing this, you trade kinetic energy for potential energy and vice versa during the evolution of the system. So there's going to be a little bit of potential energy that leaks, that makes the ball go faster and leaks into kinetic energy, and a little bit of kinetic energy that as it goes back up the hill leaks into the potential energy, and so on and so forth. So Hamilton's equations are the rules or differential equations which govern how said position and momenta co-evolve over time. And Hamilton's equations are these. Okay, and I think the thing to note is that the time derivative of the position, which we're going to eventually need to simulate the system, is the partial derivative of the Hamiltonian with respect to, the time derivative of a particular dimension or particle in our system or whatever, xi, is equal to the partial of the Hamiltonian with respect to the momentum, the potential energy of that, the momentum, excuse me, of that particle. Okay, and the change in momentum of a particular particle over time is equal to the partial of the Hamiltonian with respect to the particle's position. Okay, now these two, just try to keep these in mind while we're going through this. These two are what we need to evolve the system. Right? We need to be able to step the system by changing the position and then changing the potential energy and changing the position and changing the potential energy, so on and so forth, right? But what we have is a Hamiltonian, right? So the question is, how do we actually get a form for these that we can work with, basically? So we can verify that this is true, right? By just like taking the corresponding partial derivative. So there's a bunch of, a huge amount of literature from observational physics that develops both the Hamiltonian and establishes the rules. What we'll do here is we'll just confirm that they're true given our elementary understanding of physics and calculus. So the first one is pretty easy, the partial of h. So let's remember what the Hamiltonian is. It's the kinetic energy plus the potential energy, and those two are assumed to have these particular forms. So just keep this. I'm going to put some memory aids at the bottom of the slide, right? So the partial of h with respect to pi, well, there's no pi in this whatsoever. Pi only shows up in 1, so this is pi over m. And of course, if we assume that m is not a function of time, then we can pull the m out. That's m over m. We get dx I dt. So in fact, cool. It is the case that knowing what we know about physics and calculus, if we look at the Hamiltonian and we take this partial with respect to the momentum of a particular dimension of the system, then we get that, that's equal to the time derivative of the position. That's cool. Okay. Next one's a little bit more involved. It's not terrible, right? So let's look at what's going on here. So if we take a partial again of the Hamiltonian with respect to the position of a particular particle, and again the same memory aid is down here. Cool. So again, have to be a little bit subtle, and this calls into question or calls to the forefront your point, Emma, and now Barron's point about quantum mechanics, right? So long as the momentum is not a position of particle so long as the potential energy is not the momentum is not a momentum pi, p is not a function of xi, then this goes to 0. right? Then what you're left with is the derivative of the potential with respect to xi, okay? Now, fine. In order to get to what this is, right, this is basically the definition of a force, right? So there's a bunch of circularity in these things that's a little bit difficult to resolve, right? So here we assume that neither the mass nor the momentum of a particle of the dimension of the system is a function of the position, making the left half 0. And for our choice of the kinetic energy in the Hamiltonian case, this is an auxiliary variable. This is true by assumption. So this part being 0 is true by assumption, right? The second half is the definition of a conservative force we established before. So, and here we're looking at this component-wise. So we know that a force was equal to the gradient of a potential, and now we're just looking at one dimension of that gradient. So it's just the derivative with respect to that particular dimension. So this is Fi. Fine. But again, now we go back to our elementary physics. Fi is just mass times acceleration, right? Acceleration is dvi dt. And again, if the mass doesn't change over time, then that's dpi dt. So cool. Now we have Hamilton's equations. So the partial of the Hamiltonian with respect to the position of a particular dimension of the system, particle in the system, whatever you want, is minus Fi, and that's just minus dpi dt. Cool. And I think that gives us Hamilton's equations. Yep, there we go. So we've got Hamilton's equations. Awesome. So that's where they come from. One way of getting at them. So what do we do with them? So we have this Hamiltonian. All right, that's great. We've specified it. We've got a Hamiltonian. We have a potential energy. We have a kinetic energy. There's momenta, which are auxiliary variables, and there is the state of the system, which are the values of all of the latent variables in our program, right? And now we have Hamilton's equations, which are these laws of motion, right? Cool. And that will allow us to, these are what we'll use to simulate the time evolution of the system, right? By basically stepping the system along these, in this way, over time. So the total derivative of the Hamiltonian with respect to time is an interesting quantity and one that's very, very important to what's going on in Hamiltonian Monte Carlo. So the point is that energy is conserved throughout the ideal, and this is very important, ideal time evolution of this dynamical system. In other words, the total energy, the Hamiltonian, is constant over the time evolution of the system, right? And we can see that by just writing down the definition of a total derivative. We're going to see this in automatic differentiation in the next couple of lectures, which is just the sum over all the paths, right, of the change in the partial in h by partial in xi, and then the time derivative of xi dt, so on and so forth. Same thing on the other side. This is just the total derivative. If you've forgotten this, this is right. And by plugging in what we just derived, yeah, that's right. The dh dxi is right here, right? So that's here, and dh dp is here, and that's here. And then you'll notice that these two quantities are exactly the same. They cancel except for the sign. So this says basically the Hamiltonian is constant, okay? That's cool, right? That means that we can run, if we could deterministically simulate from this system, that means that the beginning point of our simulation and the end point of our simulation would have exactly the same probability under this joint distribution, right? which means that in order to sample from this, we could run a Gibbs sampler in the auxiliary variable sense that we were talking about before, which is we sample the momentum, and then we sample the state conditioned on the momentum by evolving the system for some amount of time. And we know that that will accept, right? That's just a given, right? So we're going to condition, basically we're going to condition on the total energy and then change the total energy. So that's really what's going to happen. So the way that Neil puts this together, and I think it's the you can go at it for a while, is to say, okay, we're going to use Hamiltonian mechanics as a proposal mechanism inside of a Markov chain Monte Carlo update. Okay. So in order to basically do this, we're going to propose a momentum, and then we're going to run a chain, right? Sorry, run the system forward in time. So to quote Neil, I think it's probably better to just use his words here. So for Metropolis updates, using a proposal found by Hamiltonian dynamics, which form part of the HMC method, the acceptance probability is 1 if H is kept invariant. So in other words, we're going to choose a momentum and then run the system forward according to time by simulating over time. If H is invariant, which is to say it has the exact same probability at the beginning and at the end. Unfortunately, this is not going to be true because we can't exactly simulate the dynamics of the system. Okay. So there are some additional properties of the Hamiltonian dynamics that we have to rely upon, and these get pretty hairy, and I'm not going to go into super high. Yeah, I'm just not. It's too much for what we need. But one thing that's relatively clear is that the deterministic mapping is reversible, right? So the position momentum pair at time t relative to another time at time t plus s, that's 1-to-1, and it clearly can be reversed by just negating the time derivatives or by flipping the sign of the auxiliary momentum, right? So that's cool if you could perfectly simulate the system. The other thing that's important, and this is the non-trivial part that I'm not going to go into in detail, we can do it offline if you're really super interested, is that the image of a region of phase space, the position and momentum, this joint, this auxiliary variable setup that we're talking about, that has been mapped forward via Hamiltonian's equations, has the same volume before and after said mapping. Okay. And this is important in proving the correctness of Hamiltonian Monte Carlo when it comes to computing the acceptance probability correctly. So we're almost there, and we'll take a break in just a little bit to let this sink in. The reality is that in order to actually use any of these equations for sampling, we'll have to numerically integrate, and that leads to errors. Okay, and the Metropolis Hastings techniques have to be used to correct for these errors in integrating the system forwards. Right. The volume preservation properties, which I just talked about, of the system, of both the system and the integrator that we're going to talk about in just a second, mean that we don't have to introduce any change of variable or additional Jacobian terms into our acceptance ratios. And that's critical, surprising, and pretty deep. And again, we could spend an entire semester talking about this, but we really want to like be able to use Hamiltonian Monte Carlo, but you should get a sense of what's going on, right? Yeah, and in order to show and prove that the resulting Metropolis-Hastings algorithm is valid and targets the correct distribution of interest, you need to go through these last steps. But in order to go through those last steps, you actually have to consider a particular integrator, right? This is the last bit of Hamiltonian Monte Carlo, and then we're basically done. The leapfrog integration method, right, preserves volume exactly, and Neil also proved this, Radford. And this is as opposed to, say, some other integration method like Euler's method. And it's reversible because of its symmetry. We can just negate the momentum, apply the same number of steps again, and then negate P again, okay? So what does the leapfrog integration scheme mean? It means that for every delta t that you run the system of differential equations forward, you update the momentum a half step, then you update the position a full step, then you update the momentum again a half step, basically. Okay, and how do we do this? Okay, so this is now the forward deterministic simulation of the system. So we're going to sample some auxiliary variable, which is the momentum, and then we're going to run the system forward. Okay, cool. So what's happening? Well, we're going to have some momentum at a particular time, Gaussian distributed, totally random at time 0. And we know, again, that so where do we need to go here? We need to go with here, dpi dt, right, is dh by dxi, but we know that that is actually equal to this. Okay, so we did that, right? So dpi dt is just the derivative of the potential at that particular point in space. So that's the force thing, right? So there's going to be a force applied by the potential field. And that's what's happening here, right? So this is the ith index of the momentum vector. And that's going to be update in a half step, right? Whatever epsilon is, by evaluating the partial of the potential at that particular, at the position that you're at currently in that, in the ith dimension, right? So we're just doing this dimensionally rather than as gradient, so it's a little bit easier. Then the position is updated, so we're going to update a full step of the position. That's going to be the position at the current time step plus the dx dt, right? And that's equal to the partial of the Hamiltonian with respect to the momentum. And that is just the momentum at that particular point in time divided by the mass. Okay? So that's what this is. And this is there. And then we've complete the step of the momentum by, again, looking at the half step momentum update and correctly applying the same rule here for the half step. Okay. So this is just a way of integrating the system forward. These are the leapfrog. This is the leapfrog integration scheme. So you're updating a momentum halfway, and then the updates to the momentum and the position leapfrog one another. Update the momentum, update the position, so on and so forth. Okay. Now, why this? Again, the reason why you have to do this is because this particular integration method preserves volume. That means that the Metropolis-Hastings ratio that you compute is correct. That means that this thing will actually sample from the distribution of interest. Done. Okay. I know this looks hideous so far, right? But it's really not, okay? Because the Hamiltonian Monte Carlo algorithm at the end of the day looks like this. So we've just gone through a huge amount of somewhat confusing stuff that requires you to actually remember physics that you don't probably remember. At least I don't every time I think about this, right? To run Hamiltonian Monte Carlo, to implement and run Hamiltonian Monte Carlo, you initialize your latent variables to something, right? For some unbounded number of steps, you Gibbs sample the momentum from the posterior distribution, like the conditional distribution of the momentum given the position, but they're conditionally independent. They're independent quantities. So awesome. That just means that you just sample a momentum randomly from thin air, right? Then you flip a coin and integrate either forwards or backwards. This guarantees reversibility of the chain, which is part of what you need to have a valid Markov chain Monte Carlo algorithm. You leapfrog integrate L steps, starting at XSPS, which is to say the position of the last sample and whatever momentum you just sampled, and you arrive at some new deterministically determined position X prime P prime, and then you accept X prime P prime with some probability associated to the Hamiltonian evaluated at the starting point and the end point of this deterministic evolution, right? Cool. And we'll take a little break here and then go back to book notation and talk about how to actually implement this in a Prog system. So let's take a long one today. We'll do 440 just, to make everybody happy.
What does it mean to integrate backwards or forwards?
Look, it's unfair because this is in the break period, so I shouldn't answer
We can
question.
wait for this, yeah.
But the point is that you can either, at the beginning, when you choose this gray vector, that's like too many leapfrog steps. But when you choose the gray vector, when you choose the momentum, you can choose to go either way. You just literally change the sign of the.
Okay.
It's a super technical detail. Actually, there's been like 20 years of arguments about whether or not you actually need to flip the sign of the the momentum vector in order to have a properly convergent, Hamiltonian Monte Carlo algorithm. I think it's resolved into the favor of yes, you do need to, but it's really subtle why you do.
Okay. It just seems a bit weird. Like, shouldn't the sampling of the momentum vector already account for?
Yeah, what you're thinking right here is totally spot on.
It's not the debate.
That's not the debate. It's like, do you exactly satisfy the detail balance, ergodicity of Markov chains in a continuous space? There's some serious mathematical heavy lifting that you have to do in order to get into that, right? Anyway, but we should stop there before we go too far. But yeah, I'll leave this up. Yeah.
It's incredibly pleasing to watch.
It's so awesome. I should point out, though, just to, as this is, I think, not hugely informational for the course. It's just extra. There are a huge number of density evaluations that take place in Hamiltonian Monte Carlo, right?
So yeah, so what I don't know, it's maybe a spoiler for some people with the homework, but it's actually, you notice that when you run the algorithm. Let me put it that way.
Yeah. Yeah. I think I can do this and talk about it while we're doing this. Like we did mention the I forgot to turn off the the recording while this break was on. Whoops. We did mention the number of leapfrog steps and like how many times you have to evaluate the density, and the fact that this is not necessarily super computationally efficient, but it is on balance relative to the number of to the amount of mixing that happens generally. Wow. Generally on balance still preferential to Metropolis Hastings, just in terms of overall efficiency, which is pretty impressive given how many evaluations take place. Another thing that can be noticed here right away is that if you set the leapfrog step to be very large, the integration scheme is such that there will be many more rejects. Right? Necessarily, you're going to do a much worse job actually, integrating the dynamics, which means that you will actually, again, just reject endpoints because the difference is too large to the original density. Let's see if we get into rejections here. Yeah, there was a rejection. Yeah.
Generally speaking, is there some principled way of figuring out what these parameters should be, or is that just?
So there's yes and no. So one thing is that most Hamiltonian Monte Carlo algorithms use a burn-in period to set the mass matrix, which is basically to learn the length scales, which is questionable. And then there are methods which I'm embarrassed that I won't be able to just remember to describe, but there are this no U-turn sampler, which came out of Columbia while I was there, and you'll notice it actually grows the chain in both directions, and it doesn't actually throw away computation basically. But so in other words, there are advanced variants of Hamiltonian Monte Carlo that we're just basically not gonna touch in the course. But in terms of setting the parameters, like what's the integration, like what's delta t, or in the notes epsilon, not really. Mass matrix, yeah, there's a lot more on that. And there's some really interesting papers from, I always want to give Ryan Adams credit for this, but I always try to give Ryan Adams credit for it, but I think it actually came out of Max Welling's group, where they use Hamiltonian Monte Carlo for amortized inference, which we'll get to in this course, and it's worth saying a couple of words about, but basically doing meta learning where the mass matrix is the thing that you learn, and for a particular problem, you in an amortized way, basically, well, we haven't talked about amortized inference, so it's a little bit difficult, but for any particular inference problem, you can somehow automatically get a mass matrix based on something about the problem description. Okay, I think everybody's back now, which is good. So back to book notation. What you need to take out of all of this, you can either decide to go down the rabbit hole if you want to, but for our purposes, what you need to be able to do is actually implement this, right? And implementing it isn't not as bad as you might think it is, okay? So again, we're used to, this unnormalized density corresponding to the Prog, basically the joint distribution with the values plugged in. That's great. Did payment go away? Yeah, looks like it. Oh well. So we have the, what I showed you before. This is exactly the same slide as earlier. We have an auxiliary variable distribution, which has the potential energy and the potential energy and the kinetic energy, excuse me, and two variables, x and in our case, r. Fine. So how do we do this? Well, we generate samples by deterministically simulating a system of evolution over time using the equations of motion. That's what we just spent the lecture talking about. So the position or values of the latent variables in the probabilistic program is updated according to this expression. So in other words, dx dt is the gradient with respect to r of the Hamiltonian, and that gradient is just the inverse mass matrix multiplied by r. Okay, so that's not so bad, right? And the change in potential energy, in our case r, is just the gradient of the Hamiltonian with respect to x, and that's the force. That's the gradient of the potential, and the potential is just the joint distribution that you compute in your program. Okay? And now you run your leapfrog integration, right, which we just talked about, basically simulating the time evolution of the system using these two in your leapfrog integrator. Right? And then you fix numeric integration errors with a Metropolis Hastings accept reject step. Okay, so you evaluate the joint, which does include the kinetic energy variable, the kinetic energy in it, i.e. this term right here. There's the joint again, right? So you evaluate that joint for the time evolved system and where you started from, and standard accept quantity, accept reject quantity. So Hamiltonian Monte Carlo, pretty straightforward, in fact, very straightforward, if you can do this. Right? Anybody want to say what that is? Not Berend.
Is it the gradient of the log of the joint?
Tis, indeed. So anybody want to say how one would get this in your Prog systems? Autodiff of what? Yes, autodiff. There is a reason why we strongly pushed you in the PyTorch direction, and for the Julia people, almost certainly the Flux direction. Autodiff of what? That's the question, right? Great. So here's the full Hamiltonian Monte Carlo algorithm. I hesitate to go through this again. It's HMC. There's an initial state. There's some number of steps. You sample, this is in the book, so you can look it up. You sample your momentum variables from, a normal. You run your leapfrog integrator. Leapfrog is right here, literally spelled out for you. And then you compute an acceptance ratio. That's it. The critical part is this, because you need it in your leapfrog integrator. Okay. Now, what is grad u of x? Well, it's evaluate something, some expression, where you stick in the current values of the system. Great. What is that expression? Well, it's an expression that you construct by evaluating all of the link functions with the values of the random variables plugged in. Right, so it's run backward on an expression like this. Run autodiff on this expression. Right, so this is a function. The way we do it, that's a function of all of the random variables in the program. These are the observes, and then we have all the link function expressions, right? And this is going to return the log probability, the sum log probability of the entire program. That's the expression that you want to take a gradient with respect to, right? And you're done. This part you should definitely ask questions about if it's not clear, because it's the second to last slide. And if you know how to do this, then you're golden. Welcome back, Payman. I think Vasilios might actually speak. I feel a question coming. Yeah. Tony? Jason? Come on, Naomi. You've got to have a question now. I still have a knot of despair in my stomach from, before.
I wish I had a question. Usually you have a question when you understand parts of it.
Okay, Baron, save me. So when you did this, did you read the book? Did you just like?
Yeah, like the book's great. So the book tells you exactly what you need to do.
Cool, that's good. It should. Does this make sense after having read the book, or is this like another one of these things where the lecture is just like, holy crap, I have to go read a bunch of stuff to understand what was going on in the lecture? Then I go back and look at the lecture and it totally makes sense? Or
no, I think this makes sense. I think, but I also think that after having done it, this makes sense to me. I think probably at this point, like, if you're a little confused about any of this, then I think you should go do it and like try to see if it works.
This is one of those things where that's what I'm trying to say. Like the whole thing, like when you like, we can look for a long time at this, right? This is what's going on, right? What do you need to implement for the third part of homework? I guess 3. It's this. Period. Right. The critical parts are that this is some big sampling algorithm that requires deterministic forward integration of a Hamiltonian, and in order to do the deterministic forward simulation of the Hamiltonian via the leapfrog method, you need the gradient of the log joint. That's what you need. Right? This is the gradient of the log joint, and then everything else is here, right? Hopefully, after listening to what we're talking about, it makes sense that you sample a momentum variable from a normal distribution, right? Hopefully, it makes sense that you can deterministically simulate the system forward using a leapfrog integrator that preserves. Basically, you can think of it for our purposes as moving along a constant energy isosurface of the Hamiltonian. Perfectly, it doesn't, so you do the Metropolis Hastings thing. But the leapfrog integrator, in order to actually follow Hamiltonian's equations, which describe the time evolution of the Hamiltonian, you need that and that. And in order to get that, you have to take a gradient of the log joint with respect to the latent variables, which means that you need to be able to construct, or rather eval, if you want, a sequence of log density expressions that you have available to you in your graphical model compiled representation of probabilistic program. The step that you're about to make, by the way, is a huge step. Like where you will, once you have done this homework number 3, be at approximately 2013 to 2017, depending on which languages you're at. Oh God. All right. So I see that you're about to become a dad, at least in terms of joke style. Great. Like you're about to write a Prog system, like that actually does the thing, does the business, and 3 different ways, which is pretty awesome. Okay.
I have a small question.
Awesome.
So this method seems like it's using so many stuff like integration, derivatives, and it also looks quite slower on like the simulation you showed us. Like, is it better than the rest? And I don't know. It's also
Okay,
like
so,
so
yeah,
much
well-
more complicated.
Yeah. Okay. Right. So, yeah. Why would it be so complicated? Why would anybody do this? It's got lots of function evaluation, so on and so forth. Well, the answer really comes back to like intuitions, and I think that's why I was like, when I found this, I was like, oh my god, this is so awesome. Let's go to random walk Metropolis Hastings. Okay. So in random walk Metropolis Hastings, remember you're going to use this as a proposal within your Gibbs sampler, right? What's the correct proposal kernel size? Are you sure that if I make the wrong choice of proposal kernel, whether it's too small, it's going to walk for a really, really, really long time before it gets? I don't know if I can mark on this. I can't mark on this. Before it gets to the lower left-hand corner of this banana, right? It's just not going to happen, right? If I make it too large, it's going to reject basically all the time. Right? So if I happen to calibrate it just perfectly, it should be okay, but it's still not going to actually move rapidly. And if you really want to compute posterior uncertainties, you want to be able to actually have samples that span the entire space. Right? So it turns out that in many, many, many situations, running Hamiltonian Monte Carlo, despite the fact that it makes all of these density evaluations, all of the black dots, ends up still actually being more efficient. When you compute effective sample size or the variance of posterior estimates as a function of the amount of computation you put in. It's very hard to beat Hamiltonian Monte Carlo if you can use it. And that's again why probabilistic programming, like STAN in particular, which is arguably really the only probabilistic programming system, non-deep probabilistic programming system that is very widely used, uses Hamiltonian Monte Carlo, because the people who use it are doing log linear hierarchical modeling where they actually want proper posterior confidence intervals because they're working on, clinical trial data where they actually have to have the posteriors properly calibrated and represented and so on and so forth. Yeah. More questions, comments? Thank you, Una.
I mean, from a Prog perspective, then why even bother implementing the other ones if HMC is going to provide a better, approximation algorithm 90% of the time?
Were you here at the beginning of lecture or no?
I was.
Great. At the very beginning? Yeah, you were. So what was at the very beginning? What's the thing that you need?
Differentiability.
Exactly, right? So would you ever want to implement an HMM? Would you ever want to implement a reinforcement learning algorithm where you make a discrete choice about something that you do? Would you ever want to implement a Bayesian optimal experiment design setup where you actually have to make a discrete choice about something? So that's why the folks from Stan would say it's the only algorithm you ever need, but they sort of overlook the fact that there's a wide variety of models for which Hamiltonian Monte Carlo can be basically arbitrarily bad in its performance.
Bad in its performance. I mean, if it's not differentiable, it's not even applicable, right?
So it turns out, and I had a 1.5 year long fight with one of my students at Oxford, which he ultimately won, about whether or not Hamiltonian Monte Carlo is applicable in the case when the gradient, when there are discontinuities in the potential. It turns out, crazily enough, that it is. it's just hyper inefficient. So the proof, like I don't even remember the details of that discussion, but it turns out that it totally is. You can run Hamiltonian Monte Carlo, but it can mix arbitrarily slowly or not at all. So
you have these sort of like walls whenever you have something that's conditional, for example, that I guess like if you imagine having some particle that rolls through some landscape, you just hit a wall and you don't get up there. Like how does that work?
no, so it's not a wall. So it's just basically you're saying you're going along. You've got a potential. Basically, the momentum is fine, right? You can have momentum, whatever. That doesn't really matter. But the potential is discontinuous, right? So that means the force exerted on the particle is going to be weird, right? So when you hit a discontinuity, you don't know what the gradient of the potential is going to be like. So you could have, one that forces you to the line and one immediately away from you that forces you away from the line, right? So in fact, you need to be able to explore right next to that line or that discontinuity. I mean, this is something that we have some optimization people in the course, strong optimization people, presumably, right? If you get into these situations where you have discontinuities, it becomes arbitrarily difficult to like explore next to the discontinuity in these kinds of situations. If you know what I'm trying to indicate with this, right? So you can think about it. Some potential. I don't know why I'm doing this in 2D. That's like this, so that your particle rolls down here. And that's totally fine, but then it hits here and it rolls way far away really fast, right? And it becomes impossible to mix along this. So like the potential is really like this. That's what I'm trying to say. Something like that. Although this is exactly flipped, right? So if you're here, you're gonna want to go in this. This is negative potential, so this is actually probability. This is a little complicated, but I'll try to do it again in a way that makes sense. If we're going to do negative, so we're going to actually do potential, right? You can have something that looks like this, right? So the ball is going to roll along here, and it should, under this, concentrate near here. Even worst case, right? Maybe it's like this, right? It should concentrate near here, but then as soon as it gets there, shoo, goes away, right? And you just have no idea what's going on.
Can I ask, like, how do we choose big T and epsilon? So like the step and the time steps. Like, is there an optimal way to choose that? Because like for the random walk, yeah, you also said like it depends on some hyperparameters, and I guess it's your sort of hyperparameters.
These are your favorite kind of hyperparameters, the ones that you have to pick after the fact, or just guess. Yeah. So small for epsilon. You can that one, that it's, if you have the computational budget, you should make epsilon small, and big for T if you have the computational budget. So it's really how much can you run? That's honestly the reason why I put the time limits in the homework, which I have no way of enforcing because we don't auto grade. But there are suggested time limits to just keep you from, like, you can set epsilon arbitrarily small and T arbitrarily large, and you'll have amazing performance, but it'll take forever, right? So there's some rules of thumb about like acceptance ratios you want to target with different algorithms. But again, the only way you can even evaluate that is you have to actually run the algorithm for a little while, and by that point for the homeworks you'll have solved the problems. So it's not worth talking about the adaptive schemes really. Namrata, you've been very quiet today, avoiding the heckling.
Yeah,
don't have any questions right now. Maybe after I read the book chapters. Yeah.
The idea, just I know all of you are busy. I'm busy too, but the idea is to read in advance of the lectures so that they land a little bit more. They land a little bit more. That would be a good thing to try. Jason, questions?
Not really for now.
Okay, great. And this, I think, is the fewest questions per lecture ever from Emma. So I'm going to ask one time, then we'll go. I guess I haven't asked Ryan either. I apologize, but yeah. Anything from you guys? You just go off and implement it now, no problem.
No, I need to understand more before I can formulate questions.
Okay, I expect
Maybe another dad joke then.
Ryan, no problem. Bang it out. Okay.
All good for now.
All right. Beautiful. Then I think we're good. Thank you very much for your time and attention. It was lovely to see you all.